The next thing we want to look at are a couple key metrics that characterize the consistency of our power supply. So if we're considering our sort of generic box here, which is our power supply, we have AC input on the left, DC output on the right. Let's look at two ways that we can characterize the consistency. The first is going to be with something called the fractional line regulation. So fractional line regulation, which we can just write as D subline. And so essentially what this is going to be doing is it's going to be measuring how sort of consistent the power supply is as our input side is changing. So as we have fluctuations in our input voltage or our input current. And so for this reason, what we're going to assume for this calculation is we're going to assume that our DC current is constant. So we're measuring these things at a constant IDC. So IDC held constant. Okay, and so the equation, I'm going to put that up here, and then we're going to look at sort of a quick example to see how we use this. So we're going to have a big messy fraction. In the numerator of this fraction, we're going to have delta VDC. So that's the change in our DC voltage, which is our output. And we'll have in the denominator of that fraction, VDC nom. And so that's just our nominal value of VDC. And so all I mean by nominal is basically the nameplate value of it. So if a power supply says it's outputting 12 volts, VDC nominal is 12. Now if we go to actually measure that, we might see that it is 12.5. So obviously that's not going to be the same as the nominal value. So in the denominator, we're going to have another fraction. And down here, we're going to have stuff related to our AC side. So we're going to have delta, the magnitude of VAC, so how much is our AC input changing, versus our VAC nominal. And again, that's going to be magnitude. And so just like with our DC, then the nominal just means that's sort of the nameplate value of what it should be. So for here in the US, we have the 120 volts RMS at a wall outlet. But as we discussed, that might vary by as much as 10%. So at any given time, we're not necessarily going to have 120. Maybe we go and measure and we actually have 117, for example. Okay, so let's look at just a brief example to kind of help see how we would use this. So let's say, as our example here, we have some DC output which averages 5 volts. So that would be our nominal value. And we have some change on the input line, which causes it to change by 10 millivolts. And so that 10 millivolt has changed due to, we have this nominal AC input of 120 that changed by 2 volts. And so we want to know what is our line, our fractional line regulation. And so basically if we sort of look at it, the question is almost sort of backwards in terms of we can think of on our AC side, we have an AC input of 120 nominally, but it changed by 2 volts. So maybe it dropped down to 118 or it went up to 122. So it's changed by 2 volts. And what that's caused to happen is our DC output, which is typically 5 volts, has now changed to either 5.01 or 4.99. I believe that's right. Either up or down by 10 millivolts. And so we can calculate our D line just using this equation. So I'll try to keep that on the screen while we plug in our values here. So we would say our D line is equal to, so of course our delta VDC is at 10 millivolts. So I'm going to put it in volts though, so 0.01 volts. Our VDC nominal is the 5 volts, that's what it normally is. In our denominator, our delta VAC, it changed by 2 volts, and our nominal value we were told was 120 volts. And so we just plug that into a calculator and we get 0.12, which would of course be a 12% value for our fractional line regulation. So pretty straightforward equation to use. So the next way that we can characterize our efficiency is something called the load regulation. And so this is sort of just the opposite. So now we're saying as we have changes in our load on our DC side, how does that affect sort of our current and voltage on our DC side as well? So this we're going to call D subload, deload. And so ultimately what this is it's going to be the difference between our no load and full load voltages, and we're going to divide that by average output. So I know that's sort of a lot to say, so let me, I guess, write down some of that explicitly, and we'll see it more clearly in the equation in a little bit. So it's the difference between our no load and full load voltages and then we're dividing that difference by our average output voltage. Okay, so if we have all these components in the equation, of course we want to look a little closer at what those conditions are. And so we're not going to go into the details of why these are this way, but for our no load condition, like we said before, obviously if we have no load, we are going to have zero current because we have an open circuit. And it would also, we could see it would turn out that our VDC is going to be V max. So now what about for our full load? So when we are fully loaded, we're saying the definition of that is that our IDC is at I max. So this could be what we sort of designed our circuit to operate at, the ID, and our VDC is going to be equal to V min. And so this might be a confusing concept of changing the load and getting different voltages from the output, because oftentimes we're just talking about ideal sources or ideal voltages, ideal components. But in practice, of course, we have a finite amount of power that can be supplied by these devices or these sources or batteries. So what that means, as we connect more stuff or larger loads, we're actually going to see a decrease in voltage. Okay, so what our equation looks like, essentially transforming what I had written up here in words and incorporating these values for our current and voltage at these two conditions, we have that our D load is equal to, so we're going to have V max minus V min, because this is the difference between our no load and our full load voltages. And then in the denominator, we have the average of our output voltage. Well, the average is Vmax plus Vmin over 2. I'm going to bring the 2 up here, and then we have Vmax plus Vmin in our denominator. So there's our equation for D load. So now just another quick example so we can see how to use that equation. So let's look at another quick example. So let's say in this case we have a nominal 5-volt supply. And so for this nominal 5-volt supply, we have been given sort of our no load and full load conditions. So we know our no load, V no load, which coming back up here, we know for no load that's going to be the same as our V max. So we can go ahead and write V max is equal to 5.05 volts. And we're told that our V full load, which again, looking up here, we know that's going to be V min. So we can go ahead and put this is V min is equal to 4.95 volts. And so what we want to find is, of course, our D load, our load regulation. And so it's as simple as just plugging into that equation up here. So we're going to try to keep that on the screen. So we just have D load is equal to 2 times our V max, so 5.05 minus 4.95 divided by the sum of the two, 5.05 plus 4.95. Plug that in and we get 0.02, which means we have a 2% load regulation. So typically these D line and D load are expressed in percents. So again, another fairly straightforward calculation. This time we're just characterizing how the power supply, how consistent it is in terms of our changes in the load. One important thing to note about these two definitions that I have boxed here, these two equations, is that these aren't necessarily consistent across the board. Some people or some textbooks will use slightly different definitions. And so sort of the caveat to using these, if you're ever calculating a D load, for instance, or a D line, is you want to verify that you and whoever you're comparing with are using the same equations. So you wouldn't want to use a different equation than a colleague who's calculating the same thing and then be really confused as to why you're getting these different results. Okay, so one other thing I want to touch on, which we have talked about in a previous class and we'll come back and touch on a little bit later in a different video as well, is this idea of ripple voltage. And so ripple voltage we've seen before is something that we get during rectification. So when we go from an AC voltage to a DC voltage, we still have this sort of AC component, unless we just completely filter that out, which is usually not practical. So this is our AC component of our DC output. And what this would look like, just as sort of a preview to a later video, of course, if we have our input is some sine wave like that, and we saw in the previous course that if we have, for instance, a full wave rectifier circuit, our output isn't going to be a straight DC voltage like we want it to be. But with some filtering, we can get it down to where it's maybe something that looks like this. And I know this is a pretty rough sketch, but you get the idea. So we have these very slight variations around some average value. And so there are different times when we are okay with having a ripple voltage, and there are some times where we really do not want to have a ripple voltage. So we definitely want to reduce our ripple voltage, which I'm just going to call VR. If we're talking about high gain amplifiers, because of course, even if we have some very small AC component that can be amplified, and then we're going to have a whole lot of this noise coming from nowhere. Another place where we typically want to minimize or get rid of this as much as possible is digital circuitry, because of course we're talking about different, depending on the circuit, relatively small margins between a 1 and a 0, for instance. So we want to be certain that this information is a 1, this information is a 0. We don't want it to be varying somewhere between those two values. So that's important there. So in contrast to that, some places where we're okay with a slightly larger VR, obviously we still don't want it to be huge, would be things like lamps or heaters, and most types of motors. And so you can see these are sort of more rugged, not as accurate applications in terms of circuitry. So one other note, sort of design note in terms of this ripple voltage, is we want to be careful of over designing. So be careful not to over design. And so what I mean by that, be careful not to over design, we know that, for instance, for lamps, it doesn't really matter if we have a large ripple voltage. So we wouldn't want to spend a lot of money to include some component in our circuit that reduces our ripple voltage if we're designing it for a lamp. Even if we're talking about a high gain amplifier, maybe we only need to reduce it to a certain point. So we don't want to go overkill to the point where we're wasting resources to reduce that ripple below what it needs to be.